Welcome to Math 31. This is a lesson on the applications of the derivative. So it's the introduction to Unit 4, applications of the derivative. And in this unit, first off, we're going to be looking at some of the common applications of derivatives that we've worked with. Now, you'll find as you go through your mathematical journey that the number of applications of derivatives is far too vast to cover in a unit like this. So I'm just selecting some of the very common things to work with, such as related rates, basic rates of change, and things like that, just to give you an idea of what some of the potential of this tool are or is. Anyways, important to remember that the derivative measures the rate of change of one variable with respect to another. So when you're dealing with a very common one, speed or velocity, velocity is really measuring the rate of change that your distance is undergoing with respect to time. Now this can be, that's a very common one, but it's true for many, many other things as well. So you will get, even in this first unit, a look at some of the variety. I will concentrate on motion ones initially, but we will branch off. Let's take a look at a diagram on this, though. So if you were to consider a position versus time graph, so I'm sticking to the proper vector notation for this. So whatever is happening with this graph, its position is fluctuating a fair bit. And if we just looked at that one spot right there, we could see that the slope is positive because of the tangent line. Now this would imply a few things. That first off, that the position is increasing with respect to time. So we would then say that v is greater than 0. So its velocity is going to be greater than 0 because v measures the rate of change of position with respect to time. So that's the idea. So if it's positive, if the slope of the tangent line is positive, it means the velocity is positive. As well, if you had something like this, we would say that the position is decreasing with respect to time. So you're moving back to the origin, if you like, or wherever you started from, but your velocity, therefore, is going to be, your position is decreasing as time passes. Now, of course, this can get complicated when you actually cross the x-axis, which we saw in some of the simple applications from the previous unit. In those cases, you're moving away from the origin because you're, but just in the opposite direction. So that's another thing like that. This is more common, and the actual velocity doesn't make the distinction, really, whether your position is increasing in the negative direction or whether it's decreasing in the positive direction, if you follow. So it can get a little complicated. And then if you were to examine or analyze the velocity versus time graph, now the shape is the same, it's not related to the original application. But if you looked at this particular point, v, velocity, is increasing with respect to time. And we would then say that the acceleration is greater than 0. So this would mean that acceleration measures the rate of change of velocity with respect to time. So if your velocity is increasing, then it means we would say that you have a positive acceleration. So acceleration in the typical physics application would be meters per second per second. So it measures what your speed is changing at. 1 meter per second squared would mean that your speed, your velocity, is increasing at a rate of 1 meter per second every second. And then if you had a negative slope of the tangent line, we would say that the velocity is decreasing. With respect to time. So in this case, acceleration is negative. So you want to be clear on what those things represent. So let's take a look at a problem, or two, or three. A particle's position, s, in meters. You will see a lot of the time that the letter s is used for position instead of d. And it changes with respect to time, t, in seconds. According to this formula, s at t is equal to 2t squared minus 1. So a simple quadratic relationship for position, whatever it is, what application it is, we don't know, or what object it is. But we want to get the object's velocity at t is equal to 3 seconds. So the first concept behind all of this is that the velocity function, v at t, is equal to the derivative of the position function, so s prime at t, which in this case would be simply 4t. And we want its velocity at 3 seconds, so we want v as a function of 3. So this is 2 times 3 squared minus 1. And then you do the math on that. 2 times 9 minus 1. I don't know why I'm doing so much work on this. So 18 minus 1 is 17 meters per second. Oops. You're wondering, what is that idiot doing out there? How about we use the proper function? V at 3 is equal to 4 times 3. So that is actually 12 meters per second. There we go. Make sure you go into the right equation. Now, of course, that's the problem with these recorded lessons. If I do make a mistake, which is easy on these ones, then I don't hear about it for a couple of days afterwards. So 12 meters per second. What I had worked out in that other equation, of course, was its position. So let's take a look at the next one. Now here we're going to move away from the basic motion problems, and just to give you another look at things. And you're going to see more and more of these volume type ones as the deeper we get into the unit. So in this case we have the volume in an oil tank after t minutes is given by this formula. So if you plugged in a specific t value into this, you would find out what the volume was exactly at that time. However, if you wanted to get a measure of the rate of change of the volume, then you would be working with a derivative. So keep in mind, what that would mean is not what the volume is, but at what rate the volume is changing. And it matters. For lots of applications, it's not so much the volume itself that we're concerned with, but we're concerned with the rate that it would be changing, which is going to matter more, just even in terms of the pressure that it puts on whatever object or vessel it's being carried in. So we want to find the rate of change of the volume's change. With respect to time. Now, it's not that bad of a question. The derivative of this one won't be too complicated. I'm going to do it at the bottom of the page. So for A, V prime at t, we don't know, we can't assign a word for it like we can with motion problems, just the rate of change. So the derivative of this function would be 2t plus 2. And at t is equal to 8 would mean v prime at 8 is equal to 2 times 8 plus 2. So that would tell me that its volume is changing at 18 liters per minute. So the volume is changing at 18 liters per minute. Minute is an odd unit to be working with because typically calculus, these type of things at least, what we're really looking for is things like instantaneous rate of change. And minute is a pretty wide, pretty long interval. It's still mathematically correct, but it's inconsistent with normal practices with these. But no big deal. And then for B, how fast is the volume increasing when there are 8 liters in the tank? Now this is interesting because it's not asking us for the rate that it's changing at any specific time value. What it's asking for is how much or how fast is it increasing when there are 8 liters in the tank. So there's quite a bit going on with this question. Now, first off, we have to take stock of which equation, or decide which equation we need to work with. We ultimately want to be finding rate of change, but because how fast is it increasing? But we don't know when that's occurring at. So we use the original formula, because this will give us the volume for specific time values. And we want to find out at what time is there going to be 8 liters in the tank. So when is there 8 liters in the tank? We solve this equation by bringing the 8 over, so t squared plus 2t minus 8 is equal to 0. Luckily, it factors well into t plus 4, t minus 2. So we get t is equal to negative 4, t is equal to 2. Now we reject the negative 4. The question didn't state a domain specifically. However, it's reasonable to think that we're talking about forward time, not backward time. So at t is equal to 2, there is 8 liters in the tank. You don't need to write that out, and that's not our final answer. But then we find the rate of change at that point, so v prime at 2 is equal to, into the second equation, so 2 times 2, because the derivative is 2t plus 2, and then plus 2. So that's 4 plus 2 is equal to 6 liters per minute at t is equal to 2 minutes. So you have to read the questions very carefully in order to make sense of these ones. And you will notice that when you do review the review assignment on it, all simple mathematics, but you have to pay close attention to figure out what's going on with it. Now, motion questions, go back to these a bit, but go a little further with them. So I'm going to bring up all the questions, or all of this particular application. The position is given by this formula, so that seems straightforward enough. It's a cubic function. I didn't bother graphing it. Graphing it is helpful, though. It can certainly tell you what's happening. And we want to first off find the velocity at a specific time value, or find the velocity period, then the velocity at a specific time, when the object is at rest, when is it moving in the positive direction, how far did it travel in 5 seconds, and then what is the acceleration. So I'm going to bring up a screen to get some space for this one, and let's go through it, question by question. So for A, question A wants us to find the velocity at time t. So we should be fairly comfortable with that. The velocity function is the derivative of the position function, so s prime at t. So I'll note that. Differentiate the given expression, and you'll get 3t squared minus 12t plus 9. And there we go. So that represents the velocity at any time t. And that makes B much easier because we want to get the velocity at t is equal to 2. So V at 2 is equal to 3 times 2 squared minus 12 times 2 plus 9. So work this one through. So 3 times 4 minus 24 plus 9. You can certainly do it more quickly than this. So 12 minus 24 is minus 12. Minus 12 plus 9 is equal to negative 3 meters per second. So this is very interesting. Now with a graph we could probably make some sense of this, but really it just means that at this point, t is equal to 2, it's either moving in the negative direction, most likely, or it is moving closer to the original starting point, or else it's moving away from the starting point in the negative direction. Can't tell just with this information, but we will be able to tell soon. And then let's go on to the next one. Question C is, when is the object at rest? So really this is, when is V at t equal to 0? So we set the velocity function to 0 because when it's at rest, even if it's just momentarily, that's when its velocity will be equal to 0. It goes from going in the positive direction to the negative direction, or whichever. So 0 is equal to 3t squared minus 12t plus 9. Now to make the factoring easier, I'm going to divide every term by 3. And I'll divide it right out. So I get t squared minus 4t plus 3. So 0 is equal to t minus 3, t minus 1. So t is equal to 3, t is equal to 1. So the object is at rest at t equal 1 second and t equal 3 seconds. So we would expect, that's S with a little hook on it, so we don't get it mixed up with position. We would expect that this thing is turning around at that point exactly. So, moving on to question D. When is the object moving in the positive direction? So, when is the object moving in the positive direction can be tackled a couple ways. But the way I'm going to do this one is, well, first off, I'm going to bring up a screen, new screen. Oops. There we go. So question D, we want to find out when is V at t greater than 0. So we take that equation that we had representing the velocity, so 3t squared minus 12t plus 9, and we set it, or we go greater than 0, set it up as an inequality. So 3t squared minus 12t plus 9 is greater than 0. And this is where we use interval analysis on it. So use interval analysis, which we did in the pre-calc section, because that's how you solve inequalities that have more than one factor in it, quadratic or higher or rational ones. So we recognize that when we factor this, I'll keep the 3 there even though it doesn't have any bearing. Based on what we saw previously, it's going to break down into this. So we set up the number line, and we take the 3 we don't need because it's positive, and we just take t minus 3. Excuse the kind of sloppy writing on this. T minus 1. And then we take a look at v at t. And its turning points are 3 and 1. So it's zeros. Those are the roots of these equations. And we do what we've been doing all along. Factor by factor, we identify where each of the factors is positive or negative, and then take the whole thing together. So t minus 3 is positive over here, negative over here. T minus 1 is positive when t is greater than 1, so hopefully this looks familiar to everybody. Negative when it's less. So the velocity function is positive when it's less than 1, negative there, and positive when it's greater than 3. So this question, we could have answered it even with, had they asked where is it negative, it would have been the same thing. But we want where it's positive, so we want there, there, and there. Now we should really also note that t is equal to 0 is the starting point. So we really shouldn't be dealing with any negative t values. Now that wasn't stated clearly in the question, so if you just answered it with no other information, I would accept either answer for it. But based on this, we can say the object is moving in the positive direction in the interval 0 to 1 second and 3 seconds forever. Now I want to be clear on this, on a couple of things. First off, the idea of writing a sentence out, not necessary, but a good idea, because if nothing else, it gives you a look at the question and you can sort of put the whole thing together, see if it makes sense. The other issue is the nature of these inequalities. Now this question didn't give us a lot of information with respect to the original domain. So like I said, when I set up a number line, I ignored everything less than 0. T is equal to 0. Now that wasn't clear, so had you gone forever to the left, you're still technically right. Most of the questions, when we get further into them, will give a domain, so we can narrow it down a little bit more. But be aware, too, that we're not at t is equal to 1, your v is equal to 0. So they are open intervals at 1 and 3. The question about 0. Well, 0 we would also assume that at time is equal to 0, that we're not including that in the interval that it's moving positive. It starts right after that. Again, kind of a debatable point, not a big deal. And the textbook is not entirely consistent with it, but that's the choice that I made on it. It should make some sense at least. Now question number E is interesting because it's how far did the particle move in 5 seconds. And we got to be careful with this because, for example, if you were to plug into this equation and find s at 5, this means the position at t is equal to 5, not how far or distance. So that's the most common mistake. You plug in s at 5 and then think you're done with it. So when we're dealing with distance, which if you're taking physics courses or have, you'd know that distance would be a scalar measurement. So it doesn't include a direction sign on it. But we have to take this position function and convert it back into a distance. So the way we do it is we note that at turning points, at t is equal to 1, t is equal to 3. And we're starting at 0. So what I do is I take its position at 1 second, and I subtract its position at 0 seconds when we start. And I take the absolute value of it. Now in this case, because it's going in the positive direction, it doesn't matter. But then, following that, I'll take the s at 3 minus s at 1. So this, by getting the difference in position, and then take the absolute value of it, you're finding out how far it went in that period. And then finally, I would take s at 5, its position at 5 seconds, subtract its position at 3 seconds, take the absolute value so I don't have any negatives, and then I find out how far it went in that interval. So s at 1, you're going right back to the beginning now, would be 1 cubed. So 1 cubed, and you can run this right through your calculator pretty easily, minus 6 times 1 squared plus 9 times 1 minus s at 0, which its position in 0 seconds is 0 cubed minus 6 times 0 squared plus 9 times 0. So that whole thing is going to be equal to 0. So when you work this one out with care, as I said, running it through your calculator is not a bad idea. I'll go down below for this one. It's pretty routine. You get 1 minus 6 plus 9. So that should be 4. And then 4 minus 0 is equal to 4. And of course, this is just the absolute value of that. So we went 4 meters in that section. And then do the same thing for s at 3. So this would be 3 cubed minus 6 times 3 squared plus 9 times 3. Now, you want to be aware that from 3 to 1, you're going in the negative direction. We've already established that. And then s at 1, we already know to be 4, because we worked it out before. And then take the absolute value. So 3 cubed minus 6 times 3 squared plus 9 times 3. Well, that's shocking news, because we end up getting its position at that point is 0. And then 0 minus 4 is also equal to 4 when you take the absolute value of it. So what has happened in that period from 1 second to 3 seconds, you're going in the negative direction, so you're headed back. And at s at 3, you are right back where you started from. And then you reverse back again. And then s at 5, we work this one out. Now be careful with it, because this is going to give you're in the positive direction again. So 5 cubed minus 6 times 5 squared plus 9 times 5 minus, well, we already know that s at 3 is equal to 0. So 5 cubed minus 6 times 5 squared, and we should get absolute value of 20 minus 0. So that is just equal to 20. So the only area, the only interval that required us to actually deal with the absolute value was the middle one. So add them together. 4 plus 4 plus 4 is equal to 28 meters. Now, one of the ways that you can draw these ones, if this makes any sense to you, is, and they do this in the textbook, is you draw these kind of loopy diagrams like this. And you note that at t is equal to 0, you start there. And this is just measuring your distance. So at t is equal to 1, you turn around. At t is equal to 3, you turn around again. And finally, t is equal to 5, you're there. Now, I haven't drawn this to scale, but you went 4 meters in the first section, 4 meters in the second section, and then 20 meters in the next section. So hence, 28 meters total. So you've got to be really careful with those. Easy to make a mistake on them. And then, just to finish this one off, I will do question F, which is pretty quick. We want A at 2, so we have to note that the acceleration function is equal to the derivative of the velocity function. So if you were to go way back to that velocity function and take the derivative of 3t squared minus 12t plus 9. Now make sure you don't do this after you've divided the 3 out, because the 3 is still part of the derivative. And you'll get 6t minus 12. So therefore a at 2 is equal to 6 times 2 minus 12. So it's equal to 0 meters per second squared. So the acceleration is 0 meters per second squared at t is equal to 2. So I'll stop there. I'm going to do, on your handout, you've got a few more questions, which you're welcome to try on your own. I will go through them, just sort of showing a bit more variety to these problems. But that will be it for now. So thank you for your time.